This video is brought to you by Captivating History. The term scientific revolution refers to two highly significant conceptual changes which occurred around the 16th and 17th centuries. Most historians mark the period between the first public printing of De Revolutionibus Orbium Coelestium by Copernicus in 1543 and the release of Isaac Newton's Philosophia Naturalis Principia Mathematica in 1687. The scientific progress made in that period was breathtaking. By its end, humanity had developed a far more accurate and valuable understanding of how the world works. However, we should not let the term revolution blind us. To most people in Europe, little had changed in that century and a half. The majority of the population continued to work in agriculture, mostly eking out a meager existence through subsistence farming. Sanitation and medicine were still woefully inadequate. Therefore, many women continued to die in childbirth. Meanwhile, most people lived in societies governed by despotic monarchies, ruling in an arbitrary and self-serving manner. These changes took place mainly in Europe. The first change was the challenge that an increasingly scientific approach presented to the then dominant religious dogma. The second was an overhaul of the core of scientific thought from one based on abstract philosophy to an empirically centered method. Let's examine the challenge to religion first. Christianity, in its institutional form, had explanations of many phenomena we would today consider the purview of science. The core of church-sanctioned answers was that God intentionally created the universe. All explanations were derived from that assumption. Church-sanctioned explanations tended to be tautological. No matter the argument or result, the ecclesiastical approach would use it to confirm the existence of God and the supreme role of the church in all aspects of life. Before the scientific revolution, science was not an autonomous discipline, but rather the outgrowth of Greek philosophy. Aristotle was the most scientific of the fathers of philosophy, and his approach was dominant for close to 2 millennia. Aristotelian science focused on the why questions of the natural world. However, modern science has mostly avoided these more profound questions of meaning in favor of the more utilitarian how question. The vast majority of Aristotelian science has not withstood the test of time. For example, Aristotle's classification of matter into water, earth, fire, and air seems downright quaint in light of scientific progress. Nonetheless, the classical philosophical approach was invaluable as a catalyst for scientific progress. It helped modern scientists frame the right questions and gave them a baseline to test and eventually discredit. The new science, which emerged during this revolution, had novel characteristics, most of which remain dominant today. A valid scientific discovery should be replicable and falsifiable. In other words, other scientists should be able to conduct the experiment and reach identical findings. The findings are falsifiable in the sense that a specific outcome would, at least in theory, invalidate the conclusions. In the service of the cause of objective truth, scientists aim to criticize and test theories and hypotheses. An easily understandable and universal language of science was needed and soon developed. Progress occurred when scientists improved upon the work of others after intense dialogue between practitioners. The replicable and falsifiable traits of science render science a community-oriented exercise. Therefore, associations and affiliations grew in 16th to 17th century Europe and later spread throughout the world. For example, the Royal Society of London for Improving Natural Knowledge was established in 1662. Meanwhile, the Académie des Sciences of Paris formed in 1666. Both received the approval and support of the monarchy, despite church suspicion. Today, epistemic communities and international conferences extend that net of scientific discovery and interaction to the global arena. But how did the scientific revolution start? In its nascence, many of the pivotal advances took place in the field of astronomy. That is no coincidence. The solar system is visible to observers, especially after the invention of early telescopes. Therefore, it is a field that encourages empirical observation and theorizing. Most notably, Polish astronomer Nicholas Copernicus compared what he saw in the heavens with the theories of classical astronomy expounded by Plato and Ptolemy. He concluded that the sun stood at the center of the solar system. This theory confirmed Ptolemaic astronomy, but grounded this heliocentric approach in a more robust theoretical system. The Catholic Church famously opposed his conclusions and insisted that Earth stood at the center of the universe. Although nothing in the Bible directly addresses this question, the Pope and his followers believed that saying otherwise diminished the importance of the creation narrative in the book of Genesis. However, generations of astronomers and scientists embraced the Copernican approach. Why? Because it was empirically demonstrable and was therefore valuable as a starting point for other theories. The investigation of astronomy soon led to advances in physics. For example, German astronomer Johann Kepler attempted an explanation of planetary orbits around the Sun. The theory required a description of the force that kept heavenly bodies in orbit and determined their movement patterns. The urgency of answering these questions led to the development of physics principles that applied to all bodies, heavenly and otherwise. Kepler should be more of a household name because his contribution to the scientific revolution does not end there. His work helped launch the scientific field of optics, which focuses on the study of light and its behavior. Using a point-by-point analysis of the path of light, Kepler invented corrective eyeglass lenses. He realized that different types of lenses could compensate for both myopia and hyperopia. His optical equations also helped explain how telescopes work and provided the basis for improved telescopic lenses. Kepler's contemporary, Galileo Galilei, used improved telescope technology to craft more empirically established theories of movement. The Italian scientist showed that the Earth was not unique in its properties and behaved much like other planets. This observation was a death blow to antiquity's astronomy, suggesting that Earth was fixed and surrounded by orbiting bodies. Inspired by the movement of the planets, a new generation of mechanical philosophers emerged. Individuals such as René Descartes were interested in the dynamics of motion and matter as explanations for a wide range of empirical phenomena. The French philosopher engaged in dialogue with Kepler and Galileo's optical theories and expanded on them. To Descartes, the light was a mechanical phenomenon. His groundbreaking approach tackled the law of reflection and contributed significantly to the laws of refraction. The Cartesian contributions to science and the underlying philosophy of science were tremendous. Among them was analytic geometry's development, which linked geometry to algebra and helped create the lexicon for future scientific inquiry. In terms of the philosophy of science, Descartes developed the question of epistemology, that is, the quandary of how knowledge can be obtained and understood. He was a trailblazer in developing still unresolved questions about the reality of matter and the dependability of observation. Since science is heavily dependent on empirical observation for data, the Cartesian sensitivity to epistemological questions has dramatically enhanced the sophistication of human perception. Another field that saw crucial advances during this period was chemistry. In antiquity, the field focused on alchemy and had semi-mystical qualities. Irish chemist Robert Boyle applied the principles of empiricism and scientific inquiry to chemical compounds and placed the field on firm footing for the first time. Using inductive reasoning, Boyle defined compounds according to their properties and carefully documented the results of their interactions. Eventually, he constructed theories, some of which proved incredibly far-sighted. For example, Boyle hypothesized the structure of atoms and molecules despite lacking a microscope. These purely theoretical concepts led the way to atomic theory and the unfulfilled biology field. These primary advances within the scientific revolution reached a climax in the work of Isaac Newton. The English scientist crafted physical explanations for the phenomenon identified by Copernicus and Kepler. To Newton, the universe was a finely tuned machine with predictable and explainable rules of motion. His rules were simple but incredibly useful. At the core of his thought, Newton argued the following. 1. Every body continues in its state of rest or of motion in a straight line unless it is compelled to change that state by force impressed on it. 2. The change of motion is proportional to the motive force impressed and is made in the direction of the straight line in which that force is impressed. 3. To every action, there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal. Using this all-encompassing theory, Newton was able to build on the advances of his predecessors. For example, in the field of optics, the English scientists challenged the notion that all colors are derived from reflections of white. Instead, He showed that white light is the result of specific mixtures of colors. He did so by separating the different elements which make up white light into their constituent parts. Newton also explained the color schemes of thin films, such as those produced by oil. The rules of Newtonian physics have since been replaced by more accurate calculations and more complex approaches. The theory of general relativity, in particular, provided a more robust alternative. However, the laws of classical mechanics aren't incorrect. Instead, they are approximations or simplifications of actual dynamics of movement and interaction. Just as importantly, they provided the basis for the development of more precise theories. Classical mechanics provided a comprehensive and falsifiable explanation. As such, the Newtonian ideas allowed generations of scientists a foil to attack and refine. If so, while many of the insights garnered during the scientific revolution are now obsolete, the methods used to obtain them were groundbreaking and of lasting import. While celebrating the scientific revolution, we must also keep its limitations in mind. First, scientific inquiry was not open equitably to everyone. At this time, scientific studies were conducted and communicated chiefly in Latin, therefore excluding individuals without higher classical education. Of course, at that time, education was the sole purview of white males of the upper class and their middle class equivalents. Women, people of color, and the poor were marginalized and kept out of universities and scientific societies. When higher education facilities became more equitable and studies were conducted and written in vernacular, women and other marginalized communities took a role at the forefront of scientific discovery. Marie Curie and Rosalind Franklin were particularly notable in this regard. However, they had to overcome incredible obstacles to achieve recognition in the field. Even today, science remains a male-dominated field. Much of the discrimination and inequality in the field can be traced to the scientific revolution. Nonetheless, the scientific revolution has benefited humanity tremendously. The result of this process was that understanding the world empirically and objectively became one of the most important goals of society. The global proliferation of universities, laboratories, hospitals, and countless other research facilities of every kind attest to this fact. How has this increase in scientific knowledge benefited us? There are almost too many improvements to recount. But ultimately, the scientific revolution set the stage for changes that would alter the lives of most of the population, often for the better. Scientific breakthroughs in irrigation and other agricultural technology would increase harvest yields and significantly decrease global hunger. In addition, the move away from subsistence farming allowed for specialization and urbanization. These changes, in turn, increased productivity and improved sanitation and medicine. Thereby, infant mortality rates decreased exponentially over the years. While in 1700, roughly 54% of children survived to adulthood, today over 95% attain physical maturity. To learn more about the history of science, check out our book, The Scientific Revolution, a captivating guide to the emergence of modern science during the early modern period, including stories of thinkers such as Isaac Newton and René Descartes. It's available as an ebook, paperback, and audiobook. Also, grab your free mythology bundle ebook while it's still available. All links are in the description. If you enjoyed the video, please hit the like button and subscribe for more videos like this.